Hello everyone. Title of this video is using the first translation theorem, or translation on the s-axis, to find Laplace transforms and also inverse Laplace transforms. I'm going to go over several examples, but first let me talk about what is this translation on the s-axis of the Laplace transform, or in this first translation theorem, and then we'll get into some examples. Alright, so here it is, the first translation theorem. Right. If the Laplace transform of some function little f of t is labeled capital F of s, and a is a real number, any real number, then the following will hold. And you can use the definition of Laplace transform to pretty easily show this. I'm not going to do that here though. The Laplace transform of that function of t, f of t, times e to the at times this exponential is equivalent to the Laplace transform of f, but where s is replaced by s minus a, so capital F of s minus a. Thus the translation along the s-axis, right? S gets replaced by s minus a, causing a shift of a units on the s-axis. Now you could also reverse this, talk about inverse Laplace transforms, and I'll do examples where both are used. Just kind of inverting this, right? The inverse Laplace transform of the Laplace transform of little f at s minus a is going to be equal to the exponential e to the at times little f of t, right? Where again capital F here is the Laplace transform of little f, right? Capital F of s. All right, so lots of letters, lots of stuff here. Let's see how we're going to use this. Now I am assuming, of course, that you remember the Laplace transform of certain basic functions like constants, polynomials, exponentials, and trigonometric functions, sine of kt and the cosine of kt, where k is a constant. Alright, so let's first start off using the top part, where I'm finding the Laplace transform of some exponential multiplied by a function of t. Right. So in this first example, and for the first four, I believe I have 4 examples here, we're asked to find the given Laplace transform. Right. So I'm asked for the Laplace transform of t times e to the 10t. So if I'm using this translation theorem up here, the value of a is 10, right? That's e to the at, e to the 10t. And then the function of t that's multiplied by the e to the at here is just t. Alright, now hopefully, again, I'm hoping you recall the following, that I'll put, hopefully you recall this, that the Laplace transform of, t, or some power of t, I'll say t to the nth, where n is a positive integer, was n factorial divided by s to the n plus 1 power. Okay. So the Laplace transform of f of t in this example, or the f of s, that's the Laplace transform of just t to the first. and that would be 1 factorial divided by s to the 1 plus 1. That's 1 over s squared. All right, so the Laplace transform of just t is 1 over s squared. And this 1 over s squared is the f of s from the theorem earlier. So then multiplying t by e to the 10t, we get the Laplace transform of this product is going to be f, right, the Laplace transform of t, but evaluated at s minus a. Or in this case, this is going to be equal to f of s minus 10, where this is f of s. So I'm just replacing s here with s minus 10. So the Laplace transform of the function t times e to the 10t is 1 over, and then instead of s squared, the quantity s minus 10 squared. And there you go. Alright, and if you want to double check this, you could try finding the inverse Laplace transform and seeing that the inverse Laplace transform of this would be t times e to the 10t. Or you could just use, you could also double check this by using the definition. Now I'm not going to do this, I'm just going to refresh your memory. Remember, this is the integral from 0 to infinity of e to the negative st times f of t. So t e to the 10t dt. And yeah. Okay. So hopefully, maybe you can even see it here, that when I put e to the negative st and e to the 10t together, this would be the integral from 0 to infinity of e to the negative, and then, s minus 10 times t, and then times t dt. So you see it's the same function, but where s is replaced by s minus 10. That's exactly what the theorem is stating. Right. Okay, sorry if that's pretty tiny there. Okay, so let's keep doing this. Alright, so again, find the given Laplace transform. I'm going to use the same rule here. Now in this particular one, we have the Laplace transform of my exponential is e to the negative 2t, so the value of a here is negative 2. And this is being multiplied by f of t. F of t in this case would be another power of t. F of t is t cubed. Alright, so the f of s, right, which is just going to be the Laplace transform of f of t, this is going to be my f of s, capital F of s. This is just another power of t, so this would be 3 factorial, which is 6, divided by s to the 3 plus 1, so divided by s to the 4th. And then according to my theorem, right, this first translation theorem, the Laplace transform of t cubed times e to the negative 2t is going to be capital F, right, this Laplace transform of t cubed, but instead of s, we have this evaluated at s minus negative 2. Well, that would be s plus 2. So when all's said and done here, this Laplace transform is 6 over, and then instead of s to the 4th, I have the quantity s plus 2 to the 4th. And that's it. And there's the Laplace transform of t cubed times e to the negative 2t. Okay. And then again, you can verify that if you wish by using the definition of Laplace transform, or take the inverse Laplace transform of this and see that you get that function back. Alright, here's another one. Again, a little trickier, but because we gotta use the linearity property of Laplace transform for this one. Here I'm asked to find the Laplace transform of t times e to the t plus e to the 2t squared. Well, like I said a second ago, you can't do that. This doesn't involve, this rule, this first translation theorem involves just a single power of e times a function of t, not this sum of powers of e, nothing like that. So I'm going to expand this, and then we'll go term by term, using the linearity property of Laplace transforms. So this is the Laplace transform of t times, and then squaring this, I'd have e to the t squared, or e to the 2t. And then you have e to the 3t, but twice, right? So plus 2 e to the 3t, and then e to the 2t times e to the 2t, e to the 4t. And then I'll distribute the t, and then again use the linearity, use the fact that Laplace transform is a linear transformation. This will be equal to the Laplace transform of t times e to the 2t plus 2 times the Laplace transform of t times e to the 3t, and then plus the Laplace transform of t times e to the 4t. Okay, now I have what I want, where I have a single power of e multiplied by some function of t. And in each one of these, that function of t is simply t, right? T times exponential, t times exponential, t times exponential. All right, and then just as we saw in the first example, then f of s, then the Laplace transform of little f of t is 1 over s squared. All right, that was the Laplace transform of t. And now all I need here is to use the translation theorem over and over again. So for this first one, it would be, f at s minus 2. All right, the value of a is 2 here, e to the at, e to the 2t, plus 2 times, and then this would be, f of s minus 3, because it's t times e to the 3t. And finally, plus, and then this last one, f of s minus 4, because it's t times e to the 4t. And just going through and replacing s with s minus 2, s minus 3, and s minus 4, we get this following sum. F of s minus 2 is 1 over the quantity s minus 2 squared, plus, and then 2 times, 1 over s minus 3 squared, so 2 over the quantity s minus 3 squared, and finally plus f of s minus 4, 1 over the quantity s minus 4 squared. And there we have it. The Laplace transform of this crazy function here, t times the quantity e to the t plus e to the 2t squared. All right, so again, but you got to use the linearity property of Laplace transforms in some cases, like I showed here, writing it out as a sum and going term by term. Okay, I've got one final example before we start looking at inverse Laplace transforms, right? The second half of my first page. And that's this one here, again, using this translation theorem. Let's find the Laplace transform of e to the 1t. All right, so the value of a is 1 here, times the sine of 3t. So the function of t that's being mentioned in the theorem is the sine of 3t. All right, now I'm hoping again that you recall the following. That the Laplace transform of the sine of kt, where k was a constant, was k in the numerator divided by s squared plus k squared. So here, k is 3. So the Laplace transform of this f of t, which is again going to be called f of s, is 3 over s squared plus 3 squared, or s squared plus 9. And then all I'm doing, according to the theorem, is replacing s with s minus 1 when I'm trying to find the Laplace transform of e to the 1t times the sine of 3t, right? This is equivalent to, according to our theorem, f of s minus 1. So, again, just take this, replace all the s's with the quantity s minus 1. So this will be equal to 3 over, and then instead of s squared plus 9, it's s minus 1 squared plus 9. And this is totally fine. You can leave it like this. Now if you'd like, you can multiply out the denominator. This will be s squared minus 2s and then plus 10. Same thing. Okay. All right. So again, hopefully you know your basic Laplace transforms for, again, constants, polynomials, exponentials, trigs, sine and cosine, right? And then, multiplying these functions by an exponential just changes the Laplace transform by replacing s with, all the s's with whatever s minus a is. Okay, so hopefully not so bad, those. All right, now I'm going to reverse it. All right, now we're going to be given some Laplace transform and go backwards. What's the inverse Laplace transform, right? What's the function that has the given transform? So that's going to be using the second half of the page here. Just reversing the inverse Laplace transform of capital F of s minus a, right? That's the Laplace transform of little f, but instead of s, all the s's are replaced by s minus a, equals e to the at times f of t, right? Where again f of t is the function whose Laplace transform is capital F. All right, so let's take a look at some examples. I've got several. First example, so again, for the last several examples in this video, I'm asked to find the given inverse Laplace transform. Okay. Well, here I'm doing the inverse Laplace transform of 1 over s plus 2 cubed. So let me think of this as f, capital F, some Laplace transform at the value s plus 2. All right, so let's say f of s plus 2 is 1 over s plus 2 cubed, meaning that f of s is just 1 over s cubed. And now I want to think, what function f of t has this as a Laplace transform? All right, well, you may notice, the denominator here is a power of s, so chances are this function is going to be a power of t. And again, recall that rule from earlier, the Laplace transform of a power of t, say t to the nth, where that's a positive integer, is n factorial divided by s to the n plus 1. So if I have s cubed in the denominator, that means n is 2. It's going to be some power of t squared. Thing is, though, I need 2 in the numerator, right? I would need 2 in the numerator, 2 factorial, to have it be t squared. So that's a simple fix. Let's multiply it by 2 and by a half. And then say what, what's the inverse Laplace transform of this? It would just be half t squared, right? 2 over s cubed. Inverse Laplace transform would be t squared. So there's f of t. All right, the little f of t, half of t squared. And now again, from the theorem here, this function, right, 1 over s plus 2 cubed, is this capital F with s plus 2 inside. So the value of a is negative 2. The value, when it says s minus a, that's s minus negative 2. And so the resulting function must be e to the negative 2t times f of t, which we found to be half t squared. So I'll pull the half out front, times t squared. So here it is. The inverse Laplace transform of 1 over s plus 2 cubed is half e to the negative 2t times t squared. Wonderful. So again, that's going to be the key, is identifying what this capital F is, so you can identify what function has that as a Laplace transform. Right? So it's involving all inverse Laplace transforms here. Alright, so sometimes they get a little trickier. This one wasn't so bad. Right? This one I could very easily see that, oh, if I just replace s with s plus 2 and 1 over s cubed, I get this function. That's not always so easy. So here's another one where you see my denominator here. I got 1 over s squared minus s plus 10, minus 6s plus 10. This denominator is an irreducible quadratic polynomial. Right? Irreducible, not factorable over the integers. Right? So irreducible quadratics like this, try rewriting it using completing the square. So watch this. Okay, 1 over s squared minus 6s, and since this is a coefficient of 1s squared here, I can complete the square on these. So I'm going to leave a little space and then have the plus 10 over here. And then completing the square, remember you take half of this linear coefficient, which would be negative 3, square it's positive 9, so I add 9 to complete the square. But just adding 9 there changes the denominator entirely, so I also subtract 9. Right. And then in doing this, we have the following. 1 over s squared minus 6x plus 9 is the quantity s minus 3 squared. And then positive 10, minus 9 is plus 1. So what I have here is the inverse Laplace transform of 1 over the quantity s minus 3 squared plus 1. And hopefully now you can see, oh, this is some function, say capital F, where s is replaced by s minus 3. This is some function of s minus 3. And if that's the case, then capital F of s is 1 over s squared plus 1. And you just saw a couple pages ago, remember that the Laplace transform of the sine of kt was k over s squared plus k squared. Isn't that exactly what I have here, but with k equal to 1? So if I did the inverse Laplace transform of this, that little f of t is just the sine of 1t, the sine of t. And the value of a in the s minus a is 3. So the function that has this Laplace transform, or when I'm taking the inverse Laplace transform, this would be e to the 3t times, and then f of t, right? E to the at times f of t times the sine of t. This function has that Laplace transform, 1 over s minus 3 squared plus 1. So again, very often you might have to do this, with these irreducible quadratics. Might have to do some completing the square to get the denominator to be in a form like the sum of two squares, s squared plus k squared, as you'll see in cosines and sines Laplace transforms. All right, let's do another one. All right, so this is pretty similar, very similar. So again, in the denominator, I have an irreducible quadratic. Now I'll let you do the completing the square. I'll just tell you what we're getting here. This is the inverse Laplace transform of s over, and then this is s squared plus 4s plus 4 plus 1. In other words, s plus 2 squared plus 1. And you can verify that that's the same denominator. Alright, now this is not a function where all the s's were replaced by s plus 2. Alright, because notice the numerator isn't s plus 2. So I'm not going to say that this is capital F of s plus 2. Now one thing you could do is do a clever little addition of 0. I would like an s plus 2 up here, so why not just add it, make it happen? But then you got to deal with the consequences. Just adding 2 up here, you can't just do that. You also would have to subtract 2. That way it's like I added nothing. And then I'll break this up, using the linearity property. So this is the inverse Laplace transform of one of these would be s plus 2 over this denominator. So s plus 2 divided by s plus 2 squared plus 1. And then I'd have minus 2. Well, I'll pull that out. Minus 2 times the inverse Laplace transform of 1 over s plus 2 squared plus 1. All right. And then we'll work with each of these separately. So in this one, this first inverse, notice that this is just some function where I could say the s's were replaced by s plus 2. And if that's the case, then that function, right, capital F of s, would simply be s over s squared plus 1. And hopefully you recall your Laplace transform rules. Recall that the Laplace transform of the cosine of kt, where k was a constant, was s in the numerator, like this has, over s squared plus k squared. So this is exactly that, but when k equals 1. So this is the Laplace transform of the cosine of t. Right, so this leads me to f of t is the cosine of t, and the value of a here is negative 2. So this first expression, this first inverse, would be e to the negative 2t times the cosine of t, right, for this first expression. All right, then the next one, I'll do it in a different color. So yes, I'm using capital F again, but this is like separate, all right? So here, again, this is like some function where all the s's are replaced by s plus 2, capital F of s plus 2. And if that's the case, then capital F of s must be 1 over s squared plus 1. And we saw this earlier. This means that the function of t, with that Laplace transform is, the sine of t. Right? The sine of t had a Laplace transform of 1 over s squared plus 1. And again, the value of a is negative 2. So what we have in this second inverse is, minus 2. That didn't go anywhere. Then this inverse Laplace transform is e to the negative 2t times the sine of t. And there you go. We are done taking all the inverse Laplace transforms. All right. So again, a little difficult to see sometimes, but hopefully you have the algebra skill to be able to do something like this. Now, another thing you could have done, this is probably the best thing. If you find some other way to rewrite this, totally fine, but I don't know, I feel like this is the best way to go about it. Alright, then I have one final example where I'm going to do another clever little trick like this up here with the plus 2 minus 2. So one final inverse Laplace transform. So again, this, you got the quantity s plus 1 squared down here, but I would like an s plus 1 in the numerator, so that way I can, say, hey, this is just like some function of s plus 1. So I'll just make it happen. So I'm going to put a plus 1 here, and then also minus 1, though. You can't just add 1 to something, right? But plus 1 minus 1 is like adding 0. And then separating these, s plus 1 over s plus 1 squared minus 1 over s plus 1 squared, we get the following. We get the inverse Laplace transform of, s plus 1 over s plus 1 squared would simply simplify to 1 over s plus 1. And then minus, and then the 1 over s plus 1 squared, so the inverse Laplace transform of 1 over the quantity s plus 1 squared. Okay. Now I guess also you could have also done a partial fraction decomposition and gotten this, but not going to get into that here. I've done it in other videos. Just know that partial fraction decomposition may come into play sometimes. Okay, now this first one, I'll do these in different colors. This is some function of, s plus 1. I could say it's a function where s was replaced by s plus 1. Well, that means that f of s is just 1 over s. And that means that little f of t, right, remember the function with a Laplace transform of 1 over s was just 1. The number 1. All right, so this first inverse is 1 times e to the negative 1t, right? If I replaced s with s plus 1, that means a is negative 1. So we have e to the negative 1t, times 1. I'll write times 1 for now and simplify it in a second. All right, so that's the first inverse using our theorem here. All right, then a different color, because it is a second, it's almost like you're starting over. In this one, again, I can think of this 1 over s plus 1 squared as some function, capital F, where s was replaced by s plus 1. Well, if that's the case, then capital F of s in this case would be 1 over s squared. And we've already seen this. That means that little f of t, right, the function with 1 over s squared as a Laplace transform is just t. Right, remember the Laplace transform of t. is 1 over s squared. And again, the value of a is negative 1. So I have a minus, right? Minus, and then this inverse will be e to the negative 1t times little f times t. And I will simplify that. I can factor out e to the negative t here. And then I have 1 minus t left over. You could do it, you could say it's this, or what I had a second ago. Okay. Fantastic. Alright, so again, lots of, sometimes, with completing the square or some clever addition of 0, whatever it is you do algebraically, sometimes you might have to manipulate your expressions to get them in some form where it's easy to identify, the function that we're talking about, the function that has that Laplace transform. And then you can find the inverse. Alright, and I didn't go over every possible scenario, of course, right? I only did 4 examples of inverse. I did 4 examples of regular. Hopefully watching over these examples help you out when you're working on similar problems. And thank you very much for watching.